other things too that I want to get done here. First of those is our land acknowledgement here, SRC. Of course, we pay our respects to the First Nations and the Métis ancestors of this land and reaffirm our relationship with one another. We understand the importance of acknowledging the past and embracing a future where Indigenous peoples and their traditions are valued and supported. Together, we strive for a more inclusive and equitable business environment that benefits all. SRC's headquarters in Saskatoon are situated on the Treaty 6 territory and the homeland of the Métis. The SRC in Regina, our office here, is situated on Treaty 4 territory and the homeland of the Métis. And SRC's Project Cleans is situated on Treaty 8 and 10 territory and the homeland of the Métis. So an overview of SRC, as many people ask what we do here. We are Canada's second largest research technology organization. We've supported industry, government, communities to develop and demonstrate technology around the world for over 75 years now. And we solve technology challenges for the industry. We commercialize technologies, and in our labs, we can test and validate those technologies from one industry to another. Often we're asked about this as well. We are a Treasury Board Crown Corporation governed by the Research Council Act, and we are overseen by an independent board of directors and accountable to the minister responsible for SRC. But our funding, a small portion of that comes from government, but the remainder does come from contract research and fee-for-service work. So for the most part, we operate just like any other business in terms of contracting. So SRC is the catalyst for your energy transition. In terms of clean energy, we work on smart grid, microgrid systems, storage and optimization. We'll have some talk about storage here today in this presentation. Oil and gas evolution, of course, we have the Center for Demonstration of Emissions Reductions, CEDAR. Carbon capture, utilization, and storage. We do some CCUS projects or things tied to CCUS, as the Hydrogen Hub report here is. And enhanced oil recovery. We've done much of that over the years in our labs. Emerging energy solutions, of course, small modular reactor deployment and applications. We were currently involved in a micromodular reactor project with Westinghouse. Hydrogen systems, of course, with this report and other reports that are coming from that. Circular solutions, biofuels and waste energy, and waste valorization. The group that I am a part of here at SRC is the Process Development Group. It provides applied research, design, development, demonstration, and scale-up of value-added processing technologies for commercial application. The group has expertise in electrical power generation, smart grids, sensor development, high-pressure, high-temperature processing, bioproduct processing, pilot plant design and operation, and techno-economic assessments. I believe as of late, we also have expertise in life cycle analysis, LCAs, which are certainly very important when we're talking about the full life cycle emissions when it comes to the energy transition. So onward now to the RMGIC Hydrogen Hub study. I'm just going to take a sip of water here. This report and study was a collaboration between the Transition Accelerator, ourselves, and the University of Regina. It was funded by the Saskatchewan Ministry of Energy and Resources, Federated Cooperatives Limited, and Whitecap Resources. They are the steering committee members, and of course involved also in discussions and whatnot the broader stakeholder group, including over 25 organizations like the cities of Regina and Moose Jaw, utilities, mining companies, agricultural companies, transportation, communities, etc. And of course, interest is open to all parties as we do these. So the RMJIC, the Regina Moose Jaw Industrial Corridor area of interest for the project, is noted by the red polygon here, that area of interest for the study, which extends from the east of Regina to the west of Moose Jaw and includes Belle Plaine. The extent of that AOI was chosen based on the available data and locations of industry and potential opportunities that could be associated with hydrogen in the region. The treaty lands and First Nations areas within the RMGIC that we mentioned earlier are also shown. And then first off, we'll get into infrastructure here. You know, one of the ways of moving hydrogen would be the use of our highways and rail networks. So shown at the top of this slide are the major highways and rail networks running throughout the RMGIC. The main highways that connect the region to Western Canada and Eastern Canada and the US are shown. The same is also shown here, as you can see, for the CPKC, or the Canadian Pacific Kansas City Railway, which runs through the Global Transportation Hub here in Regina, and the Canadian National Railway as well. Shown below are zoomed out from each of those, the main highway routes on the left, the main railway routes on the right between CPKC and CN, en route to coast of BC and to the US. Of course, opportunities could be there. Of course, we don't produce as much natural gas, certainly, as Alberta does, in terms of opportunities there for hydrogen production for export. But and as well, the US appear to be moving much faster when it comes to the development of hydrogen hubs. So it's really tough to say what that export potential might look like for Saskatchewan across the board. As well, infrastructure, just looking at the liquid and gas pipeline network from the RMJIC through to the coast of BC. Of course, hydrogen blending pilots are ongoing in Alberta, as we know. Many of us know here, at 5% blending rates. Of course, research, has shown that we may get up to 15 to 20% blending, but of course that's really somewhat site and area specific. There's more certainly things to look at in terms of using those pipelines for hydrogen blending. But with interest, Saskatchewan could look at similar pilots, hydrogen blending with natural gas over the early to midterm. But ultimately, if we're looking at large scale adoption of hydrogen for building and process heat, there would certainly have to be significant upgrades, including dedicated pipelines for hydrogen to do this. But these pipelines would also serve other hydrogen markets, including that of transportation. Looking now at infrastructure in terms of renewable power and what the potential could be here. This slide shows the annual photovoltaic potential on the left, wind speed on the right. Of course, the polygon there shows Saskatchewan here, where we are. The potential for renewable hydrogen production is decent in the region, as could be for the potential of hydrogen storage within subsurface salt caverns throughout the southern half of the province. Again, that would require much more work at this point, but we're going to speak to that a bit here as we go. But it's important to note, because the intermittency of renewable energy would require an energy storage solution. And this could be supported through the storage of renewable hydrogen in salt caverns to be used when renewables are not producing energy. So when the sun isn't shining, of course, and the wind isn't blowing. And there could also be potential for the agricultural industry here, with a third of transportation energy use in the province tied to farm machinery. So it's hard to believe, with over 1,000 medium and heavy duty trucks rolling through the southern half of the province every day, that a third of that energy use is through transportation. But we'd be showing a bit of that later on here in the presentation. So yes, infrastructure again. This slide shows the 9 or 10 major industries throughout the RMGIC that could possibly use, or at least in a couple of cases, produce hydrogen to support a hydrogen hub. It also shows the location of approved CO2 storage and approved lease of space for future CO2 storage in the RMGIC. It also points to the Weyburn-Estevan CCUS hub south of the region, where CO2 is used to support enhanced oil recovery and reduce emissions in the process. Now, if the RMGIC is to produce blue hydrogen from natural gas, that captured CO2 would also require a solution for its storage and use. So it would therefore be ideal to have a CCUS hub to support a future hydrogen hub. Now, the province, as many of you may know, only produces about 2% of the natural gas here in Western Canada. So that is a bit of a challenge. We would certainly require a feedstock from Alberta in order to do that. But in addition to trying to certainly selling hydrogen in terms of that, there's also, of course, and CCUS for the use of hydrogen production. There's also, of course, the added benefits of a CCUS hub for local industry. So early estimates, early on in the project, we wanted to sort of help in terms of the focus for the project. And so we produced some early estimates based on current energy use, and in order to help us with that. So when we break down, when we perform those estimates of total energy use throughout Saskatchewan, and then estimated the hydrogen demand based on the population within the RMJIC at 22.8% of the province, that gave us a total demand of somewhere around 601 tons of hydrogen per day. This early look suggested that our biggest wins, certainly, as you can see, could be in the areas of transportation at 43% of the total energy use, which includes mode of agriculture or farm machinery, and industry at 33% of the total energy use. Just going to grab another sip of water here, folks. So when we break down the industrial sector even further, we see that most of our opportunities in the region lie in the area of mining and quarrying, which would largely be attributed to energy use in the potash industry. And as for the transportation sector, we see the opportunities for medium and heavy-duty trucking, which Alberta and other provinces are currently moving forward on in terms of hydrogen, diesel, dual fuel trucks, and so on. Our greatest opportunity, certainly in transportation, could stem from one of our greater challenges, as I mentioned, and that's agriculture, with that third of total transportation energy use throughout the province. But it's really too big of an opportunity, or certainly too big of a challenge, which creates that opportunity to ignore. So as you could expect, the difficulty is that when it comes to the refueling of diesel tractors, much of this is done on site. So as for hydrogen, this would be a challenge over the early midterm, certainly with the cost of shipping hydrogen in trucks and the need for dedicated pipeline, and the challenge with the location of fueling stations, which would be more near the production of hydrogen, such as refineries in the region. So as I mentioned, yes, these are the traffic volumes with data supplied from the Ministry of Transport and the Sask Trucking Association. This shows that the volume of medium and heavy-duty trucks passing through the RMJIC daily is over 1,000 units. The general areas of the current cardlock diesel stations for truck refueling could also be the location of future hydrogen refueling, in particular in the city of Regina, where the production of blue hydrogen from natural gas could be within a couple of kilometers away. So keeping all of that within in close range is the idea of keeping those costs down. Looking at hydrogen production costs, this slide comes from the Transition Accelerator. They use it in some of their other materials. We've just slightly modified it. It shows that the early adoption of hydrogen fuel would also shows that it's targeting a transition from diesel in the transportation sector, at least in the early stages. Consumers pay much more for diesel per unit of energy than for natural gas or for electricity. And a retail price of $2 per liter of diesel would correspond to an equivalent hydrogen retail price of about $8 to $10 per kilogram, based on an energy efficiency of 0.86 gigajoules of hydrogen per gigajoules of diesel. So if you had a hydrogen production cost of around $2 a kilogram, this would leave you a margin of about $6 to $8 per kilogram to cover the costs of transport and infrastructure. So as I say, that $2 I'm showing here in terms of dollars per kilogram of hydrogen, shown this chart, the cost of hydrogen production as of 2022 and projections to 2030 and 2040, considering our current rate of federal carbon taxes. Most of the more common methods you'll see here for hydrogen production are shown. And as discussed on the previous slide, as I mentioned, that $2 per kilogram would be competitive with diesel, as shown on the left side of this graph. We are practically there now when it comes to blue hydrogen production from natural gas. But of course, there are other costs in terms of moving hydrogen and so on, and storage. But this graph also shows the production costs of natural gas and diesel. And since this is not an appropriate comparison in terms of comparing it with natural gas and diesel, I will show you the next slide, which shows that comparison in terms of energy units. So yes, when we look at this across the board, we can see that hydrogen is approaching the cost of natural gas production and are certainly competitive against the cost of diesel production, with the exception of hydrogen produced through electrolysis. However, this will certainly improve over time as those costs of electrolyzers improve. While options for electrolytic hydrogen include production from nuclear, the production of hydrogen via nuclear thermolysis also could be very competitive in the years to come, which would certainly bode very well for the province of Saskatchewan, as nuclear is certainly moving forward here in the province and will be more of a thing come the mid-2030s. And then again, from the Transition Accelerator, showing, as I mentioned, cost of processing and transport and fueling stations. So this shows the economics of hydrogen production, transport, and fueling stations. And between the current cost of blue hydrogen production, the processing and transport of hydrogen at upwards of 8 tons per day, and the fueling of hydrogen transport at a minimum threshold of 2 tons per day. The retail cost of around $7 to $8 a kilo is then doable for transport, as shown by the retail price target for transport, that upper yellow horizontal band on this chart. As for the target retail price for heating, we certainly will need more time in order to get to something that works for hydrogen there. I did mention underground hydrogen storage in salt caverns. This map shows the thickness of the prairie evaporite throughout Saskatchewan, from which our potash is mined. It's also a zone of potential hydrogen storage here, having been used for natural gas storage over the years. However, this opportunity does deserve more in-depth study, and it's things that we can work on here, certainly at SRC, to evaluate the ultimate opportunity and the potential to support a hydrogen economy. As I noted previously, of course, this storage will be critical to large-scale hydrogen production, especially when it comes to supporting the intermittency of renewable energy. The chart on the right in this slide shows the depths and associated working gas pressures ideal for salt cavern storage of hydrogen, and our salt caverns here in Saskatchewan typically check both of those boxes, at least as a starting point. So then a deeper dive in these next couple of slides in terms of hydrogen demand. When we did this for the report, this factored in the area activity in the RMGIC as opposed to solely a percentage of the population of Saskatchewan. Just going to take another sip of water here. So shown here, by 2028, of course, 98% of that demand will be attributed to industrial feedstock, as it is now, for oil refining and fertilizer production in the region. Of the 2% attributed to fuel, nearly half of that is estimated for the transportation sector, as they are among the earliest of hydrogen fuel adopters. Considering that demand for hydrogen fuel, the total is estimated at around 16 tons per day by 2028 between industry, transportation, and commercial and residential applications. Now we look at estimates for hydrogen demand by 2035 based on area activity. That demand jumps to roughly 146 tons per day, with a greater share of demand attributed to fuel at 16%, and demand increasing in the industrial, commercial, and residential sectors. In the transportation sector by 2035, through the estimates of the 51 tons of hydrogen per day estimated for the transportation sector by 2035, most of that falls under long-haul transport, medium or heavy-duty trucks, and freight rail. So as mentioned, hydrogen diesel dual-fuel truck development and pilot demonstrations are well underway, certainly in Alberta, and a transition to 100% hydrogen fuel cell trucks will likely follow as we have the infrastructure in place. CPKC, Canadian Pacific Kansas City, already has 3 hydrogen fuel cell trains in Western Canada, with plans to bring on more. So as I mentioned, yes, we need to be looking at CCUS opportunities here, because where there is a potential to produce blue hydrogen from natural gas, there is a need for a regional CCUS hub to support a regional hydrogen hub. So in the case of the RMGIC, this could tie into the Weyburn-Estevan CCUS hub in southern Saskatchewan, so the area of Boundary Dam and EOR with Whitecap, CO2 EOR. So with a connection via pipeline, potential producers of hydrogen in the RMGIC could send their CO2 to support emissions-reduced oil production in the province. A CCUS hub could also support other industries throughout the RMGIC to do the same, and to reduce the current 3.5 million tons of annual CO2 emissions between the top 9 emitters in the RMGIC, as is shown on the top right corner of this slide. So then we look at potential demand in a low emissions future. So taking 2050 roughly is the time frame for that. Total demand of 776 tons of hydrogen per day, shown here, could represent a market potential of over $700 million per year for the region. That would be, of course, at a wholesale price of $2.50 per kilogram for hydrogen. Expanded to the entire province of Saskatchewan, that total market potential in a low emissions future would be about 2.7 billion per year, again, based on that 250 per kilogram. As the transportation, power generation, and building and process heat markets reach 45% of hydrogen demand by 2050, the subsequent emissions reduction would total roughly 5 megatons, 5 million tons of CO2 annually. So as I mentioned previously, we are currently at about 3.5 megatons between the top 9 industrial emitters in the RNGIC. So here's a bit of a recap or a cover of some of the challenges and opportunities, because as we know, with everything we do in the go forward for our energy of the future, which would include oil and gas, of course, and everything that we are working on now, there are certainly a number of challenges and opportunities there. So to go through the left-hand side, the challenges, right? We're looking at the current retail cost of blue hydrogen. The retail cost today, blue hydrogen in the RMGIC, so somewhere $5 to $7 per kilogram would, as I mentioned, would only be competitive in a transportation market. This assumes about 5 kilometers of dedicated pipeline from a natural gas production source. So again, being close to the production of hydrogen, as could be the case in the east side or east end of our province here, near the FC of operations. Power generation and building and process heat markets would require, a total retail cost of $2 to $3 per kilogram to be competitive, as we know. Adding salt cavern storage for an increased scalability would also require another additional cost. So the economics certainly are a challenge go forward. Hydrogen properties, energy efficiency, right? Efficiency losses from the multiple transfer of energy is certainly challenging when using electrolytic hydrogen for grid storage. Losses from production from electrolytic hydrogen and conversion from hydrogen can range anywhere from 30 to 80%, and some of those sources are noted in our report. And this is partly due to the very unique physical and chemical properties of hydrogen. The gas has a remarkably low volumetric energy density, requires considerable work for compression, significant space for storage, and energy for pipeline transport. Of course, other challenges on infrastructure. We would require, as I mentioned, significant infrastructure development to support hydrogen fuel markets. The transportation market would require 6 to 7 fueling stations right now to satisfy transportation estimates that we have for the RNGIC demand to 2035. And pure hydrogen markets for backup and renewable power and building and process heat would also require dedicated pipelines and compressors, not to mention upgrades as mentioned. So there's a number of challenges there on infrastructure. Hydrogen supply and demand. Saskatchewan is also challenged, as I mentioned, in terms of blue hydrogen production, with only 2% of all the natural gas in Western Canada. So we would certainly, in the early to mid stages, looking at blue hydrogen, we'd be looking at acquiring some feedstock from Alberta for that. And another challenge here is investment tax credits, federal investment tax credits. The clean hydrogen ITCs do not apply to projects with carbon intensities greater than or equal to 4 kilograms of CO2 equivalent per kilogram of hydrogen. So there would certainly be considerable investment needed for the development and deployment of CO2 capture. As I mentioned, CCUS would be very important in the early to mid stages here. But on the other side, of course, we have our opportunities. And so, we have an opportunity here to leverage a regional CCUS hub south of us to accelerate low carbon hydrogen production. And so we need some continued investment in this, and it's very critical for that hydrogen hub development in the RNGIC. As I mentioned, those hubs south of us and the newly approved geologic storage, as I noted in the presentation, could certainly be leveraged to accelerate that production of blue hydrogen. We have potential for CO2 storage here, as we know, in Saskatchewan. And the region is estimated to have 3 gigatons of regional CO2 storage space in approved and operating geologic storage projects and EOR projects south of the RNGIC. And about 250 gigatons have been noted as P50 for CO2 storage throughout the province. In terms of hydrogen storage potential, of course, we could have potential here in terms of, as I mentioned, in terms of salt cavern storage, and that is something that would require further work, and certainly SRC would be very interested to work on something like that. Medium and heavy duty road freight are also other opportunities here. Those trucks, when we're talking classes 5 through 13, they account for nearly 40% of all the transportation on Saskatchewan highways, with over 1,000 units, as I mentioned, passing through here. And of course, there's also opportunities for motive agriculture. Comes with challenges, but of course, it's again, given the amount of energy use in the province, it's really a bit too much to ignore. Dedicated pipelines, yes, another challenge, but there are certainly opportunities in that. Local steel manufacturers here that are in Regina are very interested in the development of safety codes and standards for pure hydrogen pipeline that would certainly be designed to resist embrittlement, which would be one of the concerns for using current pipelines that are in the ground. And they are also working on projects tied to CO2 pipeline and other projects related to CCUS and the future of low carbon hydrogen production. We have certainly some of the best solar and wind resource potential, as I noted. And, this is possible that we could produce low carbon hydrogen production during times of peak production and for use during off-peak periods. Of course, the other opportunity that we could have as we get into the 2030s would be that from nuclear, producing low carbon hydrogen from electricity or via heat from high temperature electrolysis or thermolysis. We also have in the report noted a hydrogen hub development checklist. So again, in the near term, the idea would be to leverage existing CCUS infrastructure as noted, and initiatives, pilots such as the Hydra, H2 diesel fuel, and the Aztec projects ongoing in Alberta, and also H2OEL, which is the hydrogen project, fuel cell project with CPKC Limited, initiating pilots into hydrogen power from farm equipment, such as hydrogen dual power tractors that are currently being developed and being tested in Europe and other areas. Pre-plan for fueling station development in the RNJIC would be ideal now. Initiating detailed studies into regional salt cavern storage potential, as I mentioned. The development of dedicated hydrogen pipeline, also mentioned, and developing hub project selection criteria, which would include plan, scope, cost, and commercial potential. Midterm to 2035, advancing that hydrogen pipeline from testing and safety standards to manufacturing with early production to support fueling stations, accelerating H2DF and HFCE medium and heavy duty trucks from demonstration to deployment, so hydrogen fuel cell. Furthering any CCUS infrastructure development for hydrogen scale-up and engagement with industry. We should be accelerating the development of hydrogen fuel cell technology for power generation, leveraging existing infrastructure for hydrogen blending pilot projects, and the development of hydrogen from renewable energy, biomass gasification, and of course, new nuclear. Revisiting the potential for hydrogen buses to support city bus fleets. As we know, the city is moving more forward in the near future here on electric buses for their fleet, but there may come a time when we can revisit that in terms of something that may require a longer travel time around the city, and incorporating opportunities for hydrogen use in municipal bus fleets. Some of that, of course, is noted in the report. And over the long term, accelerating that development of dedicated hydrogen pipeline, again, shifting more primarily to hydrogen fuel cell for medium and heavy duty trucks from hydrogen diesel dual fuel units as they are approaching end of life, and fueling infrastructure would be more readily available for that. Transitioning hydrogen development for all sectors to hydrogen fuel cell technology where applicable to reduce emissions associated with combustion, supplementing that low emissions blue hydrogen with production from other low carbon sources such as renewables and nuclear, and investigating export potential pending supply, of course, from combined low emission sources. So again, folks, before we finish up here, we always welcome you to connect with us. You can reach me here in Regina at the information provided. Of course, this presentation will be on the Canadian Hydrogen Association website following this, so you can get that information there. So at this point, I'll stop sharing my screen, and if you have any questions, we'll be more than happy to do our best to answer them.
Everyone you'll be able to turn on your mics and cameras now. Please feel free to raise your hand and we can call on you.
Hi there. This is Rashid from Evras. Um, One of the things that I would like to know um, for the current phase, the short term 2028, and of course the midterm as well, you will be focusing more on green hydrogen or a mixture of everything. Sorry, you are mute.
All right. Sorry about that, folks. I accidentally hit the wrong button when I finished my presentation and dropped out and had to come back in again. So yes, the early to midterm, we'd be with those lower volumes certainly, we'd be looking at more of the production of blue hydrogen from natural gas in the region, and that would certainly be likely more readily available for us at that time. And then as we move into the later stages, of course, higher volumes required as we get into the mid 2030s and beyond, there could very well be opportunities from the nuclear industry that would be here at that time in the province. But of course, that would be really dependent on what they're doing at that time. But yes, the earlier stages to mid stages would be from blue hydrogen.
We have a question in the Q&A chat. Are you storing the hydrogen in liquid or high pressure gas for these stations?
Okay, I'm going to call on Dave Lazell as we work with him, Transition Accelerator with this. I'd like to get some take from Dave on what might be the advantage of one over the other.
Yeah, so I mean, in the analysis that you presented, we actually analyzed three different kinds of stations. We had looked at compressed hydrogen being going to the stations and being stored from like tube trailers. That's typically for stations under 1 ton a day, half a ton a day, something like that. And then the liquid hydrogen that would be brought to the station, but it would actually probably be expanded to a compressed gas at the station, and or it could be, theoretically the liquid hydrogen could be stored at the station and only expanded when it needs to be transferred to the trucks. That was the least expensive for the stations. It's the most expensive hydrogen because it has to be chilled to minus 200 and 250 degrees Celsius or something. But it's, so it's least expensive though, because you avoid a lot of the cost of compression, right? Um, we also looked at a pipeline delivered hydrogen where you're having perhaps only at 20 or 40 bars by the time it arrives at the station. So you got more compression. That's the most expensive station, but the cheapest hydrogen. So it's a trade-off, right? And the fact is that I think the numbers that David Anthony presented on for the study sort of allows for all three kinds of stations and the whole value chains. One of the most interesting ones, though, is the possibility of liquid hydrogen on board trucks in the future.
Yeah.
And there's a lot of interest in that. And that would allow trucks to go perhaps, to achieve ranges similar to our diesel trucks right now,
Yeah.
where you'll be onboard storage of liquid hydrogen. And personally, I see that as being perhaps even a cheaper station, but if you're going to
Yeah.
have more refrigeration equipment at the station, right?
Well,
And I think
and
that's maybe where we're going in the future.
Okay, that's because that's very similar to the way LNG is today. So
Exactly.
I was wondering if we are going to be going that way because so a little bit of my background. I was part of the European International Hydrogen Project way back in the mid-aughts. So I know that was actually a huge thing when BMW had their 7 Series and they were riding on liquid. And us guys here in North America were like, how the fuck are they doing that? Because we were doing 700 bar, 350 bar, and then fast fill at like 12,500. And like, do we really want the kid we're paying minimum wage to be handling a 12,500 PSI hose that you're going to plug into that? And then like just designing components for that and everything. So I was like, having that background and then working for Air Liquide and having the liquid storage there, I was like, okay, where is the finances coming towards that? And like, I worked on the Blue Road in Quebec, which has the LNG stations on there. And the issue for us was more, like bringing the liquid hydrogen there and more, it wasn't, the storage and like the insulation as well. Because if something starts leaking, it's actually really easy to band-aid it, but to actually really fix the problem takes a lot of work. So, yeah,
There's
okay.
a lot of technology, I think, going to be developed, and Daimler is very active. A number of
Yeah.
European companies very active on hydrogen, liquid hydrogen on board trucks now. So
Yeah.
I think that's area is going to be moving very quickly in the next few years.
Yeah, because we've done stations based on electrolyzer technology and down in Ontario where we work. So that was interesting. But so the fact that liquid can now become an option, I'm like, oh, that sounds really exciting because it's a lot more efficient storage wise.
Absolutely. Yeah.
Cool. Thanks for my question.
Thank you. I noticed there's a question here in the Q&A. Does the provincial government have a funding mechanism in place to support pilot projects? Not that I'm aware of. However, if you certainly for all the funding that could be available for hydrogen and other projects, related projects, all of that is noted in the report. So again, if you go to the Transition Accelerator website, download the report, you'll see at the very end of the report is a list of and a short description of each of the funding that could be available for such projects. There's also a question here around any specific plans to build fueling stations for hydrogen locomotives. Nothing specific, but I did hear. Oh, go ahead. Oh, that that may be the interest from CPKC, from what I understand, maybe more in the Moose Jaw region. So that would certainly be opportunities there for that region in terms of the use in the RMJIC. Just reading another one here. Oh, go ahead.
Oh, sorry. I was just going to read this question. Go ahead.
Great to see you again. What are your thoughts of ammonia as a storage vector for trucks and then cracked on board to produce hydrogen? Quite fitting for a place like Saskatchewan, no? Dave, I'm going to turn this one over to Dave Flazel again, our Canadian expert.
Actually, it's an interesting question. I think ammonia on board, ammonia is toxic, which is pretty nasty. But the nice thing is it's like propane. It can be stored in a propane type tanks. Is a lot easier to store and move around than hydrogen. At minus 33 degrees Celsius, it's essentially a liquid, whereas minus 253 for hydrogen. There is a company called Emoji that has a conversion technology, probably one of the better conversion technologies for taking ammonia back to hydrogen, and then so the hydrogen is clean enough that it can be put through a fuel cell to generate electricity on board. And I think those companies like that are moving fairly quickly now to make ammonia as an energy carrier. I think ammonia's got a bigger opportunity on farm because, especially in Saskatchewan, a number of the farms on the agriculture sector are used to handling ammonia. They know how to work with it. And there's even actually some interesting opportunity. I'm on another group committee looking at on-farm production of ammonia from wind and even solar on-farm that would make their own hydrogen, make their own ammonia on-farm. And there's a company out of Waterloo, Ontario, that is actually starting to deploy some of these in Manitoba, on-farm ammonia production and essentially then using it as a fertilizer and potentially a fuel in the future. So exciting opportunity. We're not quite ready for full-scale commercial deployment yet. So
yeah, but there are pilots. I believe Dave too. I noticed as I was working through this for ammonia diesel dual fuel tractors in the U.S. right now. Ongoing. So
absolutely.
So we're getting there. And when we talk about that's certainly one of the challenges here, right? When we're talking farming, but again, a big opportunity. We could look at, I guess, on-site hydrogen production. If you can't get it there from renewables or nuclear-based production, that could be then transported by truck, at least for the early to mid-terms, and in terms of piloting something on the farm.
Yep.
Another question in the chat, why not produce excess power using SMR to produce green hydrogen? No CO2 to deal with.
Right, so I think we made some reference to that here. Certainly producing electrolytic hydrogen from nuclear certainly be a a way of the future for hydrogen here in the province, and certainly in the mid-2030s and go forward. And other opportunities that the Canadian nuclear laboratories have been working on for over a decade now, and those references are noted in the report. If you want to download that, would be for not only electrolytic hydrogen from nuclear, but for thermochemical. And so even more competitive in terms of costs once that gets up and running. And so lots of opportunities there for the future for hydrogen production here in Saskatchewan.
The next question is, how much hydrogen is currently produced in the region? I think we addressed that, but
we addressed that one, yeah, because this question came up. So that would be, again, going back to the earlier slides here, in terms of what and most of which, remember, I noted most of which, 98% of that was for feedstock for industry here, not so much for fuel or anything of that nature. So yeah, so again, all that information is in the report.
great. Could you speak to some of the risks of using salt caverns for underground storage?
Oh, okay. Yes, there certainly are risks that we would have to look at if we're thinking of using salt caverns for storage for anything, and certainly for hydrogen with the size of the molecule and the ease of movement through any cracks or crevices or anything in rock. But we're talking salt caverns, you know, if they were fairly homogeneous in terms of, you know, just only salt, there's certainly a lot less risk. But once we get a case where we have interbeds of clays and other material, that's where we can have escape of gas. So those are some of the concerns we should have, and of the cavern walls and collapse and that sort of thing. So all of these things should be investigated on a case-by-case basis. Is it possible? Yes. But again, they have to be, each one has to be taken individually and looked at and studied in terms of, there are certainly things we could do here at SRC in our labs and other projects we could do to look at that. On the high level, I do know from some other work we've been doing on the side that in areas like China, where they have lots of opportunity for salt caverns, they have done plenty of natural gas storage in the past and are now working on both hydrogen and compressed air energy storage in their salt caverns. And a very high level look, my background in geology, I did a high level look on their caverns in terms of the well logs and in terms of sonar images. And on a comparison, what we have here in Saskatchewan actually looks better in terms of competent rock and competent salt caverns. Again, so that's good for you know, for a start. But again, each case would have to be looked at case by case basis to ensure we have a proper storage.
Great. We have another question from Brody in the Q&A chat. Could you comment on the potential for solar energy to produce green hydrogen? Any idea on a reasonable percentage of future demand could be met by solar hydrogen in Saskatchewan?
Yes. Again, you know, most of that production in the early stages would certainly come from blue hydrogen, and then the potential for nuclear in the mid-2030s. Yeah, I don't have anything in the report as to say how much of that may be from renewable energy. We do, all I could show was certainly we do have lots of potential in terms of, you know, the sun often shines here and the wind does blow reasonably here in the province. The other piece, again, as mentioned, you'd have to consider with that is the possibility of storage. So there are a number of things to look at there. So I wouldn't be able to comment on what that number could look like. It would require much more work in terms of the storage piece to be able to do that.
And Dave, any thoughts on how hydrogen might work for motive agriculture to replace the fueling of diesel tractors on site?
Right. Another question. I think Dave, both Dave Hazel and I mentioned that. Yeah. Again, as mentioned previously, you'd be looking at, you know, because of the challenge we have now, of course, we don't have the pipelines to get that there. So in the early stages, if you're looking at a pilot, you'd be looking at getting it there by truck, for example, for the pilot. Because of course, yes, there is the challenge. We're not able to fuel on site as with diesel. Hydrogen diesel dual fuel would be ideal early on, or as we mentioned, the ammonia diesel dual fuel. So at least in cases where you couldn't get the hydrogen, you'd be able to use 100% diesel. And so those are some of the things that we could do, certainly in early to mid stages. At such time that we'd have more dedicated hydrogen pipelines, of course, things would certainly be much easier. Dave, any comment on that? I think we covered it already.
I think most of it. The only other comment you might make is that if we already have natural gas pipelines to farms, for example, agricultural areas within Saskatchewan, many of those pipelines could potentially be converted to hydrogen pipelines, especially in the lower pressure side of it. In which case, then you could have hydrogen delivered by pipe. We just take over the natural gas network with hydrogen. In a net zero future, of course, distributed combustion of natural gas is going to be problematic. So those pipelines could become available. We're talking probably late 2030s, 2040s here in the transition. So it's not something that's in the early stages.
And we have another question from Mitch. Are there any concerns about water consumption for large-scale electrolytic hydrogen production?
Yeah, I mean, that's, again, with everything we do here in the energy transition, there's a give and take, right? So in order to produce that hydrogen, correct, we got to be looking at what does that mean in terms of water usage. It's not unlike anything else we do. So that's where maybe other opportunities, certainly in the earlier stages, from natural gas and from thermochemical processes with nuclear, may be able to reduce that water usage. So there's other opportunities there. And of course, natural hydrogen production, other things could be out there as well that could. So it's not all about one. It's about a combination of everything is really, as we have to look at everything in the energy transition in order to get where we need to be in terms of supporting the economy and the environment.
Do we have any other questions? Please feel free to turn on your cameras and mics as well.
But again, while if there's nothing else there, while we're here, I'd like to thank again those who funded this project, and certainly to yourself, attorney, and folks at the Canadian Hydrogen Association, as well to Dave Blaisdell for joining us today. So many of you know Dave. Many of you may know Dave, as he's our expert here in Canada.
Well, if we have no more questions, I will give 7 minutes back to everybody's day today. I will give out the recording and the slide deck by the end of the day. You'll receive an email. And if that's all we have, and I would like to wish everyone a great day.
Right.
Thank you, everyone, for attending.
Thank you.
Thank you.
Thank you. Bye.